Hello, Science fam. Today we're going to be looking into concentrations of solutions. Now remember, we've learned that a solution is a homogeneous mixture, meaning that everything is completely dissolved. That solute is dissolved into the solvent. And also remember that solutions can be liquid, solid, or gas in a mixture of all three. So once we get that in mind, now we can start looking into the phenomenon of concentration. So let's get to it. Looking at concentration, it really thinks about how much solute is dissolved in solvent. So if you look at something and we say that the solution is dilute, it means that there's only a small amount of solute dissolved into the solvent. So when we look at this diagram below, as we go this way, things are becoming less and less concentrated. So we'd say that it's becoming more and more diluted. So a dilute solution means there's just not that much solute in the solvent. So for coffee drinkers, this would be like a weaker cup of coffee. There's like more water than actual coffee grounds in the drink. It's dilute. The opposite of that then would be more of a concentrated solution. A concentrated solution on this chart shows going to the right, that things are becoming more and more concentrated. What does that mean? Well, in the picture, you see that it's becoming more and more darker, but the reason it is because there's a larger amount of solute dissolved in the solvent. So this would be more like, again, for coffee drinkers, a stronger cup of coffee. There's more coffee grounds in the drink, which makes it a darker, more robust, full flavor. So concentration is important to us because it helps us figure out how much is actually of the solute dissolved in the solvent. When we look at solutions, we can talk about another way of how concentrated they are by what we call their saturation. So if we say that a solution is fully saturated, what that means is that you have dissolved so much into that solvent that you can't dissolve anymore. For example, if you took a cup of water and you started putting salt into the water and stirred over and over again, there eventually would become a point where that solution would be saturated, meaning that no matter how much you stir the water, no more of the salt will dissolve in the water. So we call that saturated. To think of it in a metaphor, think of like a wet towel and it's been dropped in the bathtub. That towel is completely saturated. So if you use that super soaking wet saturated towel to dry yourself off after a shower, it wouldn't help. You'd still be wet because the towel could no longer absorb any more extra water. So because of that, we'd say it's saturated. That's what can happen with a solution. A solution can have so much of the solute dissolved in there that it can no longer dissolve anymore. So anything extra, if you added that salt and it was a completely saturated solution, the salt would just fall to the bottom and not dissolve in. So we call that saturated. Because we're talking about concentrations, you might not be saturated. You might have a solution that's considered unsaturated. An unsaturated solution means that there's still room for more to dissolve. So if we go back to that cup of water and you've dissolved the salt into the water, now if you added more salt to the water and stirred it up, all of that salt would still dissolve, meaning that the solution is unsaturated. There's still room for more solute to be dissolved in the solvent. So this could be like a fresh towel that's dry and you dry yourself off, no problem. It absorbs the water off of us after a shower. Or it even could be a slightly damp towel. The towel could be damp, but still there's enough room in that towel to absorb more of the water. So it's unsaturated or not completely saturated. So again, lower concentration means it's probably an unsaturated solution. You can add more. Higher concentration, if you add so much, it may become fully saturated. There is one little goofy phenomenon called supersaturated solution. Occasionally, you can set up a solution. Again, think of something like, I don't know, water, and we're heating it up really hot, and we add a lot of salt to it, and it's dissolving. And as we slowly cool down that water, that solution might be holding more salt than it should. So occasionally, solutions can hold a little bit more solute than it should. And usually what happens as soon as any little thing changes, you touch it, you move it, you change the temperature at all, a lot of the crystals fall out of solution, kind of like a snow globe. But anyways, occasionally a solution can be called supersaturated because it's holding more than it should due to the conditions it was under. It's very unstable often, and will often, once something changes, again, like movement, someone touches it, or the temperature changes, from there a lot of that solute will fall out of solution, kind of like a snow globe. But I wanted to make sure you were aware of that term. Now, there are quite a few different ways to measure concentration, but the first way that we are going to measure it, which is going to be the most common in our classroom, is called molarity. And by the way, molarity is labeled with a capital M when it's in its mathematical equation. But to find out molarity, this is a way to measure concentration. All it is the moles of the solute that were dissolved in the solution, okay, divided by the liters of the solution. So if you look at it, you're going to take moles of the solute divided by liters, so the units for molarity become moles per liter. Or you can just use the big capital M as well for the unit also. But let me do an example problem that can help us out, I think, a lot. Let's take a look at this practice problem. It says we have 35.60 grams of magnesium iodide. Okay, so right away that's given to me. 35.60 grams of Mg I2, magnesium iodide. And it's dissolved in enough water to make about 470 milliliters of the solution. Okay, so we know we have 470 milliliters of the solution. We want to know what the molarity is. So we're really looking for molarity. Well, we know that molarity is going to be the moles of solute divided by the liters of solution. But here's the problem. We don't have moles of solute and we don't have liters of the solution. We have milliliters of the solution and we have grams of the solute. Remember, since this magnesium iodide is the thing that's dissolved in the water, it's the solute. So we're going to need to convert both of these so that we can get this properly plugged into our equation. So let's do that. I'm going to erase a couple things to make some room. Okay, are we ready? This is what we're going to do. First thing I'm going to do is I'm going to take my grams of solute and I'm going to need to convert it back into moles of solute. So it's coming back to us. We're going to use our mole map once again. So if you recall, if I'm going from mass A to mole A, I'm going to put grams of the substance on the bottom, and we know to do that because the grams up on top are going to cancel with the grams down at the bottom. And we're also going to put moles of the object up on top because that's what we're trying to solve for. All right, so when we look at our mole map, for every 1 mole of the substance, we're going to need to put the molar mass of magnesium iodide. So how do we do that? Do you remember? What we do is we look on the periodic table and we're going to take the mass of magnesium. Magnesium, according to my periodic table, is 24.31 grams per mole. And then I'm going to add to that 2 iodine masses. So I'm going to look on the periodic table. Iodine is 126.9 grams for each. So I'm going to add that up twice. In case you needed to see that, magnesium iodide then, magnesium is 24.31, and each iodine is 126.9. So I'm going to add up all 3 of those. When I get my answer, it gives me 278.11 grams. Okay, so remember, the reason that the mole map does this is grams of magnesium iodide cancel out, and that's going to allow us to get our answer in moles. So what I'm going to do is 35.60, right, the first number, then you multiply by the top, times 1, and divide by the bottom, which is 278.11 grams. That is going to get me 0.128 moles for my answer. So good news, I now have moles of solute for the top. All I have to do now is convert my 470 milliliters into liters. If you recall, there are 1,000 milliliters in a liter. So what I'm going to do is my dimensional analysis. I'm going to put milliliters on the bottom to cancel out, liters on top. And I know for every 1 liter, there are 1,000 milliliters. And you can look that up if you didn't remember, but that's something we should probably know. 1,000 milliliters in a liter. So that means I'm going to do 470 divided by 1,000, and I end up getting 0.47 liters. Okay, so we've got a lot of information here, but this becomes really straightforward. I've got my liters of solution. I've got my moles of solute. Let's do our equation. Molarity is equal to, up top, moles of solute, so 0.128 moles on top, and divided by liters of solution on the bottom, which is 0.47 liters. So when I divide those two, let's put it in the calculator, 0.128 divided by 0.47, and the final answer I get is molarity equals 0.27, we'll say with rounding, molarity. So you can either do 0.27 moles / liter or just 0.27 capital M moles. But in the end, that's how we figured out the concentration according to what we call molarity. And that's how we actually get to do a problem. So a solution that has a higher number in the M means it's more concentrated. It means there's more solute dissolved in the solution. If we have something with a lower number, that's going to be considered something that is less concentrated or more dilute because it has a lower molarity. So the way we would read this out loud is this is a 0.27 molar solution. And again, with more practice, we'll get better and better with that. But at least now you have an example of that. We're talking about concentrations, and molarity is the first way we're going to calculate it. We have other ones coming up, but we'll stop there for now. All right, science fam, thanks for hanging in there. Let's try some molarity problems and go from there, and we'll be able to answer questions in class 2. Take care.